Dr. Mattingly. William, the floor is yours.
Thank you so much. And thanks for having me here today. Just give me 1 minute to make sure I got everything set up correctly. And I think everyone should be able to see this now. I'm going to be talking today about large language models in the age of NLP, and really the question that frames all the conversation today. And I'll set up some time at the end for questions. Is should we even bother learning natural language processing in 2024? Why not just use something like ChatGPT, which is probably the most popular and familiar large language model to everyone? And hopefully, the big takeaway from today are a few different things. One, I'm kind of designing this talk around the idea that the audience comes from a lot of different backgrounds, predominantly in the humanities, and might not know a lot about machine learning. So, we're going to talk a little bit about machine learning, what it is. We're also going to talk about large language models very conceptually at a high level. And most importantly, we're going to talk about some of the key limitations of them. Maybe you've heard the term hallucinations. We'll learn a little bit about what hallucinations are, what kinds of hallucinations there are, and why they exist, and how to kind of mitigate them in some kind of pipeline or workflow. And then we're also going to learn about how to use large language models, specifically with humanities data. And I'm going to be bringing in some examples from my personal work with the Holocaust, South Africa, and multilingual corpora or collections of texts. And really, the big thing that I hope we all kind of take away from today is that large language models are part of a solution. They're not the solution. So one of the biggest challenges that we always see as humanists is people just taking large language models and just trying to apply them to all problems the same way. And we as humanists really pride ourselves on the close reading of primary sources. So today we're going to learn a bit about how LLMs are not necessarily very scary and these hallucinations that can occur, but potentially very useful if we know how to use them in a workflow in the right way. So letting them be part of a solution, but not the solution. I always like to start these talks with one general question. What is machine learning? And so I thought we could take away the mystique of machine learning a little bit by first looking at a single picture. This is a picture I find that I can teach machine learning with very effectively. So if I were to open up the chat right now and ask everyone in the chat just to post, what is this a picture of? What animal are we looking at? What would you all say? And feel free to type into chat. Penguin, penguin, penguin. On down the list, we're seeing penguin. And here's what's amazing about this. We as humans have lived probably several decades at this point, if not at least one. And yet all of us have been able to identify this as a penguin with one big caveat. This penguin doesn't exist in nature. Like you've never seen this penguin before. And yet all of us could easily identify this as a penguin almost instantly. And the reason why you were able to do this is what we call experiences. And these experiences over time have allowed us to look at this and say pretty quickly that this is a penguin. Now, why were we able to do that? Well, we can look at it and it's got the features of a penguin, right? It's got two different colors. It's got the black and the white that we oftentimes associate with that tuxedo look of penguins. It's also bipedal, so it's walking on 2 feet. It also has the characteristic beak, and it's got the general features of a penguin. And this is how machine learning essentially works. We're able to give machine learning a bunch of examples of real things over time, and hopefully through experiences of seeing different kinds of penguins with the label of penguin associated with it, we're able to teach a machine learning model to recognize the different features or characteristics of a thing and then let it predict on really what we call out of scope data or edge case data. So data like this penguin that doesn't exist in the real world or in nature, or data that we as humans have never seen before, but are able to generalize on or make predictions on effectively. And this penguin allows for us to really understand how that works. So imagine giving a computer system a bunch of examples that it can learn from through these experiences with the appropriate labels to eventually pick out the things that align with that particular label and letting it learn how to do classification all on its own. So real quickly, that's what's kind of happening behind the scenes with machine learning. Now, there's a lot of different types of machine learning. What we've just described is what we would call supervised machine learning, but we also have other things like unsupervised and semi-supervised. But I want to jump ahead real quick and talk a little bit about what natural language processing is. So that's kind of the cornerstone of our talk today. So what is NLP? Well, NLP is really at its root the ability to automate the processing of language, oftentimes in the form of text, through some kind of computer system. We have a lot of different ways that we can do natural language processing. Up until a few decades ago, this was done entirely through what we call rules or heuristics, where we could have different tables that would align certain things to certain categories depending on certain custom conditions. And these conditions would be written out manually. Over the last 30 years or so, this has been gradually changing from a rules-based field to what we call a machine learning-based field, where different algorithms are used to automate a lot of these processes. Essentially, we allow the algorithms to learn from different experiences or labels to learn the features of text so that it can align labels correctly. And a great way to understand how this works is to consider this one basic sentence first. John went to Paris on the 1st of August in 2023. Now, if we were to think about this single text, very simple text with only a few words, and I were to ask everyone to identify what we call the entities in the text, to do named entity recognition, we could all probably do it pretty well. And we might do something like this. This is an NLP task, a natural language processing task called named entity recognition. The goal of named entity recognition is to take in some kind of text input, such as a simple text like this, or maybe an entire book, and automate the process of finding the relevant pieces of information that align to certain classes or labels. And this is a task known as classification. And in named entity recognition, or NER, we would want to align John to a person, Paris to a location, and probably the 1st of August 2023 to a date. This is one kind of task that NLP allows for us to do. We also have other NLP tasks, such as text classification, where we can classify a text as a whole, not the individual tokens or words in a text. We also have ways of identifying and classifying the parts of speech. So John being a proper noun, went being a verb, and also assigning its essentially its technical grammatical breakdown. So what kind of verb? Past perfect verb. And we can assign different parts of speech to everything. All of these are different ways that we can use natural language processing to understand a text or some kind of input string more deeply and more effectively. And the goal of NLP is to automate this entire process with the understanding that there are going to be some mistakes in them. And this has been a well-held and well-accepted caveat of the field. But the big question is, why use machine learning for this at all? Why not just come up with a list of rules and write everything out? And realistically, you probably could. Those of you who might be familiar with regular expressions or regex might already have seen formulas that can easily identify all cases of dates in the English language. In English, we really only have maybe 12, 15 different ways that we can render a date, which means we can realistically write complex rules that can capture dates almost 100% of the time, assuming that there's no typographical errors, and maybe doing a little bit of data pre-processing when we send a text into what we call a pipeline. And likewise, locations. They can be a little easy to identify. We could easily cultivate what we call a gazetteer or a list of all the different cities across Europe, and this could find Paris and flag it. But the problem becomes a little bit more complicated when we start thinking about this sentence more deeply. Paris functions very clearly in this example as a place. And how do we know that Paris functions as a place in this sentence? Does anyone have a guess? And feel free to type into chat if you want to. We have the preposition to. And in context here, so context is important as well as this preposition. We're able to see very clearly that Paris functions as a place. But what if we said John went with Paris on the 1st of August 2023. Now Paris functions a little differently. Most likely in this scenario, Paris is a person because traveling with someone is something that we frequently do. So again, context can change how things function grammatically in a sentence, and most importantly, what the label is for a specific kind of entity. And this is why we can't just write rules for everything. Language is far too complex to just have a large collection of rules. It needs to have some other way to learn the features and assign labels correctly. And this is where machine learning comes in. It can look at these different contexts and alter these labels based on those contexts. And we're going to see particularly why large language models are good at solving that kind of a complex, challenging issue. But we also have the example of John here. Now, while we're using John with just a single name, it seems pretty straightforward to use rules to classify John. You could easily make a list of all these different names. But names are different and they're structured differently across the world. Most importantly, we sometimes have first names, middle names, and last names. If you're in a Southern Spanish or Arabic culture, you might have a very long name that describes your lineage as well as your own personal name. So names are very complex and they can change a lot in a lot of different texts across time and space. And that means that you can't realistically write essentially a giant list of names and expect to practically label all names. You can, however, with just about a few hundred examples or so, get a machine learning model to recognize the features of what a name actually is for a person and get it to label it fairly consistently and accurately. And this is why we oftentimes use machine learning in NLP. The big question is, though, with the new technology on the block, is where do large language models fit into this workflow? Everything I've really described up until this point has been what we call kind of more of a traditional model where we're using all these different examples so that the model can learn the features of a particular label. But where do large language models fit in? They're a little different. Large language models are, well, they're large. They're what we call foundational models, and they're technically generative pre-trained transformers. The real benefits of large language models are that they can be fine-tuned to some specific task. And this is done through either fine-tuning them directly or through the providing of them with different kinds of examples. And when we provide a large language model with examples, this is known as some kind of shot learning. Either we don't give it any examples and we just describe what we want this large language model to do, in which case we're describing zero-shot classification or zero-shot learning, or we can provide it one example of what we want the large language model to do. And this is known as single shot or a few examples, which is known as multi-shot or a few shot learning. And we'll learn a little bit about each of these as we kind of dive deeper. So when we say that large language models are large, what are we talking about here? Well, we're talking about large in a lot of different ways. We're talking about the size of the training corpus. Large language models see trillions of terabytes of data, and this equates to billions of words as a minimum. Um, Oftentimes, if you're looking at something like GPT-4, we're talking about trillions of words. And so this means that we have many, many, many texts that these models are able to look at and learn from. Well, how is this done? It's done through what we call semi-supervised or unsupervised learning, where the model is able to essentially see all these texts and just start to learn how words relate to one another in different contexts. And over the course of a long period of training, it's able to train on large amounts of hardware. So many tens of thousands of GPUs in the case of GPT-4 over the course of many months. It's able to learn very deeply language and how we as humans use it. When we also talk about these models being large, we're talking about the size of the model and oftentimes parameters, usually in the billions of parameters if we're talking about LLMs like the latest versions of Llama that just came out or GPT-4. So oftentimes in these larger ones are going to be 405 billion parameters plus. When we talk about parameters, what we're talking about are different things that can be activated inside of the language model that contain some kind of information when processing data. So when we talk about these models being large, we're talking about them also being very large to essentially run. because the more parameters you have, the larger the hardware that hosts that model needs to be. And this process is what we call inference. So the key takeaway here is that the ability to understand these large language models have the ability to understand language very broadly, but really at the expense of compute. And that equates also to energy and specifically large amounts of GPUs. But let's take a look at how the large language model really kind of alters the landscape of NLP. So let's consider this example real quick. Imagine we had a collection of texts, so a corpus of news articles. And our goal is to take in these news articles. So maybe they're going to deal with food, sports, and politics. And our goal is to classify each one of these. So traditionally, we would use a text classification model for that step. But imagine we wanted to do other things. Imagine we wanted to be able to identify all the people, the organizations, and the dates. Imagine if we wanted to also look at the comments, because this is all digital, and identify if the comments are toxic or not toxic, so they can be flagged for review or possibly removed. All of these things, each of these steps really require traditionally a different model. For the first example, we would use what's called a text classification model. To train this, we would provide maybe about 10,000 examples of food, sports, and politics, all labeled by humans. That takes a lot of time to do. And then we would train the model to recognize the features of those three categories. Likewise, we'd also have to manually annotate examples of people, organizations, and dates. And for this, we would train a named entity recognition model. And then finally, if we wanted to be able to identify toxic or non-toxic data in the commons, we would train what we would call like a toxic model. Technically, this would be just a binary classification model. So in order to do all this, we have to spend a lot of time cultivating the data, training the model, and then running the model. And all this can take, if you're depending on the complexity of the problem, many months to actually do effectively. And the big reason why is because of the time it takes to annotate the data necessary to train these models. And the more labels that you have on a project, this would be very simple in this case, the more complex the problem becomes. It requires you to really think through the schema or the data model that you're coming up with for how you want to annotate the data. Large language models really flip this in a new, different way. A large language model functions as what we call a foundational model. And what this foundational model is it's a model that was trained on, like we saw a second ago, large amounts of data across the web. Now, why is this important? Well, a large foundational model has all the benefits of a broad understanding of language, which means it knows all these different features inherently. It's already inherently learned what food is, what sports are, what politics are. It's learned what people, organizations, and dates are. It's learned what bad behavior and good behavior is, just from reading all these different texts from humans, and a little bit of guidance as well. And this foundational model can be leveraged by simply providing it with fine tuning. And this is where we use just a few examples, maybe 100 instead of thousands, to fine tune a model to a particular task. And we can use the exact same model, fine tuned, to classify food, sports, and politics. We can use the exact same model to be fine tuned to classify people, organizations, and dates, and likewise toxic and non toxic. In other words, a large language model allows for us to really reduce the amount of time it takes to perform one of these tasks. But more importantly, we don't even need to fine-tune these models in a lot of cases. We can do what's called zero-shot classification, where we just tell the model to do this task. And in many cases, if the task is fairly simple, it can do it. We can also use few-shot or multi-shot classification, where we give it one, two, three, four, maybe five or six examples of different tasks, and we give it examples of how we want that task to be answered. And that same model can be used for all of these different tasks with very few examples. Now, the big question that should be popping up in your mind is, why not just use the large language model then to do everything? Well, there's a big reason for that. And it comes down to some of the inherent limitations of large language models. And this is where I want to have most of our discussion be today. So what are these limitations? Well, I think a good way to understand them is to really start with a guy named Fredegas of Tours. So Frédéric of Tours was a medieval philosopher. He lived predominantly in modern-day France, just southwest of Paris. He traveled a lot within the court of an emperor in medieval Europe called Charlemagne or Charles the Great. And he's alive from about 780 to about 834. And he's not a very well-known figure. In fact, if I posed Fritigus of Tours to a lot of medievalists, they might not know who he is because he really only wrote one treatise. He lived a rather obscure life. He only is mentioned in about 8 different sources. And he's only mentioned oftentimes in one sentence. So he's not super well known across the different primary sources. He did, however, function as a signer on a witness on Charlemagne's will, but that's his one famous document that he appears on. So, why is Fredegus a good example? Well, we can use Fredegus as an example to understand LLM's limitations. So imagine, and this is a real conversation that I had with ChatGPT-4, and if you try to recreate this conversation, you might have a slightly different experience. But I posed the question, when did Fredegus go to Prague? And GPT-4 was actually very good. It said that Fredegus of Tours, a Carolingian scholar and abbot, never went to Prague, and it goes on to explain who he was, why he was important. This is the kind of answer that you'd expect from an LLM. But with very little prompting, you can say something like, yes, he did. And sure enough, ChatGPT is happy to recognize its mistake, even though it was right the first time, and goes on to explain how Fredegus or Fredegesius did indeed go to Prague. He was dispatched there by Emperor Charlemagne in 806. And it goes on to explain this very believable scenario in which Fredegus goes to Prague. All of this is completely fictional. Fredegus never went to Prague, no primary source even hints that he ever went to Prague. But this is really believable because Charlemagne had a lot of business with Prague. He conquered the region. Fredegus was connected to Charlemagne. He was a witness on his will, and he even was in his court for about 10 years. So, in the timeline, the 806 timeline, also aligns with what he's done. And he did function in a teacher capacity, likely in Charlemagne's school around this time period. So contextually, this is both very believable and very close to being accurate, but completely and totally fictionalized. Now, why is this example important? Well, it details one very clear thing, a hallucination. This might be a term that we've heard, but I want to spend a little bit of time talking about hallucinations today because it's going to address how we can kind of solve them and where LLMs fit within a workflow. Because if these things can't hallucinate, and they can hallucinate, and they will always hallucinate because of how they work when they generate data, if they have the potential to hallucinate, then how can we safely use them as humanists if they're going to generate fake data, especially if we work with very sensitive data like I do, which deals oftentimes with the Holocaust? Well, let's first understand what hallucinations are. There's a lot of different kinds of hallucinations. There's contradictory hallucinations, when it's kind of what we saw there, where it contradicts the prompt as a whole. There's factual hallucinations, where we also saw a factual hallucination with Fredegus, where Fredegus didn't actually go to Prague. These are probably the most common and most familiar hallucinations to most of us. There's also incoherent hallucinations. And this is where the model just kind of generates mostly stuff that's indecipherable. It doesn't really make a lot of sense. And these are less and less common today. They were more common with GPT-2. And most of even your open source large language models that are smaller really won't have incoherent hallucinations, with the exception of what we'll see in a little bit known as vision language models or multimodal models that are working with audio and text or video and images and text. But for the most part, what we have to worry about as humanists is number two here, the factual hallucination. And the reason why we have to worry about that is because these factual hallucinations look very believable. And so much so that possibly most medievalists, if they didn't investigate that hallucination closely, might believe it because it aligns with a lot of what they know. But as a person who is maybe one of 100 people who studied Fredegus closely, I happen to be very familiar with his life and know that that's not true at all. But it requires a detailed knowledge of this to be able to pick up on. So let's see a little bit more about factual hallucinations and really why they occur. They occur for a few different things. One comes down to the training data, so that the data that that foundational model saw when it was learning about language, because this is going to be what affects its knowledge of the world. Another thing that can affect it is temperature. which is a parameter that we can pass to a large language model that allows it to be more or less creative. And then finally, context can really change how a model shapes and frames what it says. And we'll see a lot about context today. So first, let's talk about training data. So training data could have inaccurate or false information. This is very common because a lot of this data was scraped from the web indiscriminately, especially early on, and just kind of used to train these models with the idea that if we give it tons of data, it'll be able to generalize and figure out what's true kind of on its own. Now, there's a lot of steps that are in place that really kind of help weed out some of this bad information. But things that are a bit more tricky to work out of large language models are things like outdated information. This is particularly problematic because these models take so long to train that oftentimes by the time they come to the public, the training data that they were trained on is maybe 3 to 6 months old. This is especially true for open source models. There's also sometimes a low diversity of sources. So we see predominantly Western languages, specifically English, have a disproportionate representation in a lot of these data sets. We also have things like noisy data. So think of bad OCR, optical character recognition. So stuff from archive.org, for example. And we also have data that can be misleading or biased because a lot of this data is coming from the web. And as many of us probably know, the web is not the nicest of places that has a lot of biased data on it. But we also have a lot of inaccurate information and false information. So let's talk a little bit about that. For instance, we might have inaccurate information on the web. And I think a really good example of this is to use one specific example. Imagine we were to type into ChatGPT right now, to have another language is to possess a second soul. And I guarantee you, if you put this into a cloud, if you put this into GPT, it might give you a thing that says this is attributed to Charlemagne. But at least a few months ago, when I was testing this extensively, it consistently said that this was a quote that Charlemagne said, an emperor in Europe who we just talked about a second ago. The problem is this is a completely fictional quote that I have no idea. I think it starts around the 1800s to be attributed to Charlemagne, but it's completely fictional. It's dated to 1,000 years after his death. And yet, if you were to type this into one of these large language models, especially the open source ones, you're probably going to get consistently that this is a quote attributed to Charlemagne, or this is a quote that Charlemagne said, even though it's completely fictional. And while this is a simple example of just a quote misattribution, it demonstrates the much deeper issue of we don't know what these models are oftentimes trained on, so we don't know what kind of inaccurate or false information that might come out of them. But we also have outdated information. So oftentimes when we're working with a model, we might have data that really is up to about 2020 or maybe 2022. And so a great way to think about this is to ask the question, who won the Stanley Cup in 2023? And if you're working with a model up until maybe about a month ago, but if you're especially working with open source models, you'll get an answer, but it likely won't be the right one. And this is a good example of outdated information. But we also, this is an example of when I actually did this because these are generative models and they're stochastic, which means that they're going to have very randomized outputs. This is an example of it actually being wrong. In fact, it was the Vegas Golden Knights that won and not the Florida Panthers. But we also have low diversity sources, and this means that we also have a lot of biases in these large language models that are particularly skewed towards the Western English-speaking part of the world, and specifically in countries like the United States and Britain. So if I were to ask the question, who was the mayor of Fort Myers in 2022, I would get the correct answer. And the reason for this is because Fort Myers, despite being a very small town, appears in the United States, it appears on Wikipedia, and it has a pretty detailed presence on the internet, despite being a relatively small city within the United States. But if I were to likewise pose the question, who is the mayor of Teeswaterskloof, and this is a very small village in South Africa in 2022, I would get an answer that was not right. I would get a hallucination, or I would get an outdated response, or I would get a response that looked like it could be right because it uses South African names, but is totally fictional. This is a good way to demonstrate the biases of low diversity within these large language models. And so the big question is, the big thing to take away here is essentially we don't know what issues exist within these large language models without testing them extensively. And that can be very challenging to do. And the reason why we don't know these things is because oftentimes with the best models that are closed source, even some of the open source ones, we don't know exactly what they were trained on. And so the only way to find these biases or these issues is to test them extensively. And oftentimes that's highly impractical. So the big question is, how can we use them realistically and safely within the setting of the digital humanities? And this is where I think a lot of the work I've done over the past few years can be really helpful. I'm going to spend about 15 or 20 minutes going over some of these examples, and then I'm going to save time for us to ask questions so we can kind of dive in to the areas that might be more relevant to the audience here today. So I've broken down for us for today, really the different ways I see large language models being useful. And the big takeaway I hope that you have today is that no matter how you use large language models, there should be what we call a human in the loop, a human that is always validating anything that these models generate. As we've seen, these models have the ability to hallucinate and produce incorrect information. And this information can be very believable. And the more sensitive data that you're working with, so if you're working with data from maybe apartheid era South Africa or the Holocaust, the more vital it is to make sure that everything that this LLM is doing is correct and accurate. And the way we do this is we use the model, but we use the model with a human who is validating the outputs. Now, why would you want to do that? Well, we'll learn a little bit about why in just a second. Another use that we have for these LLMs is what we call synthetic data. Synthetic data is data that we generate, and it's completely fictional. Now, there's a lot of different use cases for synthetic data, and we'll dive into a couple of them in just a moment. The other thing that I've broken down for us is what we call improved discoverability. There's a lot of instances where we're working with multiple languages within our primary sources, and we might not always have those languages, especially if we're maybe assisting an undergraduate student who hasn't yet taken the language courses necessary to do what we would call, working with primary sources at like maybe a master's or a doctoral level. And this is where LLMs can really shine in solving what we call multilingual problems. But they also are shifting over the last year or so towards solving what we call multimodal problems. So these are multiple modes of data. So think of text as one mode of data, images as another, video, which is a sequence of images, audio, etc. And they're also really useful when it comes to metadata curation. I work a lot with archivists, so we're going to dive in and talk about that. And then finally, what I hope we have time to talk about today is linking up responses that are generated to factual based material. So what we call primary sources by giving them that kind of context to generate a more accurate response. So we'll talk about this process called retrieval augmented generation. So model in the loop or human in the loop is the first thing I want to talk about. This is where we use a model to help us do a specific task. Imagine that we are working with a collection of texts that are maybe not simple like this. John went to Paris in 2024. Maybe it's data that's associated with the Holocaust. And we want to go through and we want to annotate maybe a collection of diaries. And we want to find any instance where there's a person reference to concentration camp, a ghetto, maybe a specific vehicle like a train, which is very important for research. Imagine we wanted to be able to annotate all these things, but there was no model that existed for doing this. Well, one of the things that we can do is we can load up a large language model and have it annotate each text, each diary individually. And as it does that, we can go through and make corrections. Now, why is this important? Well, if we look at the text on the left, we see that the model generated everything correctly. And we see that John is person GPE, which stands for geopolitical entity, is Paris. Because we again see the two here, we have date for 2024. So all this is right. But on the example on the right, we see that this LLM has made a mistake. It's identified Paris still as a geopolitical entity, instead of considering the possibility that Paris in this context is maybe John Paris or Ted Paris, so John's sibling. John just happens to have the surname or the last name of Paris. Or maybe he went to Paris or went somewhere with Paris Hilton, and it's just referencing the first name. And so Paris here can function also as a person. So model in the loop allows for us to get the benefits of a large language model, But by having a human going through and checking the outputs and making corrections, so adjusting GPE here to person, we're able to get the benefits of the model without the potential for hallucination. And how do we do that? Well, we can use what we call annotation software. And a good one I have found in the past is Prodigy. It costs money, but there's plenty of other ones out there that are free. And they allow for you to use large language models to visualize how the model is annotating the data. And then they allow for you to make the manual corrections. And this is again model or human in the loop. And it's been particularly useful for a lot of different digital humanities projects that I've been on, where we don't have a model at the start of a project, but we need to cultivate training data pretty effectively and quickly. And we can do this also now by using both closed source and open source models. We can identify and create what we call data models and an expressed schema using frameworks like Pydantic. And so we can define exactly how we want an output to appear, what we call structured outputs, by defining this as classes or as data structures in Python and passing these along to the model. And we can tell the model, this is how you should structure the output so that we get consistent and reliable outputs from the model. This is very important for a lot of tasks, especially when it comes to taking the output from the model and aligning it to tokens in a text to assist with labeling. But we also have the ability to use models to generate what we call synthetic data. And this has been an area of research really for the past, I would say, year. We've seen a huge push in the direction of synthetic data. Now, why is synthetic data so appealing? Well, if you have a good workflow for generating synthetic data, you can generate what we call highly augmented or varied data with very minimal effort and very little time that can be used to train other models or fine-tune a large language model further or cultivate really large data sets very effectively in minutes or hours instead of months or years, depending on the size of the data set. So why would you want to do that? Well, it helps us solve a couple different problems. Oftentimes, when you want to build a machine learning model to do something, it can be really hard because of legal limitations or because of ethical reasons to get real world data to train a machine learning model. So synthetic data and using a model to generate synthetic data, which is what this is on the right-hand side, can allow us to effectively generate data that looks like what might appear in our primary sources, but we don't have to go out and label it and annotate it ourselves. Synthetic data also lets us solve a very common problem with machine learning. Oftentimes, when we're cultivating real world data, we have an inherent imbalance in our labels. So, for example, in working on Holocaust data, we might have a lot of the times Auschwitz, Bergen-Belsen, Dachau all appearing as concentration camps. These are some of the larger ones and the ones that are referenced most frequently in our sources. But we also have a lot of smaller ones that appear in the sources too. Synthetic data can allow us to essentially create more data of those smaller concentration camps that appear so they can have a boosted appearance in the training data. But likewise, if we had a label that appeared disproportionately at a less level, so imagine we had 1,000 occurrences of the label of concentration camp or place and dates, but we didn't have a lot of examples of people, or we didn't have a lot of examples of vehicle appearing in our data. And that just happened to be the data that we selected for annotation. One of the things that we can do is we can use synthetic data to boost the examples of the underrepresented labels so that we can ensure that our labels in our data set are equal across the board, which really improves the model that's trained on that data set. We also have a really good reason for using synthetic data for ethical reasons. So you can imagine that if you're working with really sensitive data, you might not want to use that data as training data for a machine learning model. Because oftentimes when we make open source models, we want to open source the data set that we used. Here's a good example of where this was recently important for us. We're working with a collection of 250,000 very personal letters from South Africa. These are all handwritten. And we want to use this data to train a machine learning model to recognize personal information in these letters. So things like personal names, things like personal experiences. Oftentimes, these were written by women who are detailing very intimate moments in their life. Sometimes they're dealing with miscarriages, sometimes dealing with affairs, sometimes dealing with their children. We wanted a way to be able to train a model to recognize these kinds of sensitive moments in the letters, flag them, and mask them. Now, the big problem was we wanted to make this data set open source so that others could train a similar model on other data, but we could not, for ethical and legal reasons, use the original data. So the solution that we developed was to use a large language model to generate fake data. The letter on the right does not exist. And the reason for this is because I cannot show you the letter on the left. The letter on the right is completely fictional. It details completely fictional places, fictional experiences, fictional people. Everything was generated by a large language model. This data contains personal information that we can then use as training data to teach a model to flag information when the text on the left is converted into raw text, so that we have a model in place that can annotate things that we need to be annotated without having to use that original data for ethical and legal reasons as training data. And the other reason why we might want to use synthetic data is because it allows for us to fine tune a model or train a model very quickly and effectively. Within about an hour, I can have a data set of 10,000 examples, and I can fine tune a model an hour later that's much better at doing a specific task. In other words, the way we started today was by talking about a task that might take months to do with tens of thousands of examples with a lot of human labor. That can be completely condensed down into just a couple hours, realistically, or maybe even a day. There's some more issues that kind of come up that need to be adjusted, which is sometimes the case. In other words, large language models can be really useful in this area of synthetic data. They're also very useful at multilingual NLP. So I'll talk real quickly about an example. We were working with Whisper, a audio speech recognition machine learning model, and we transcribed a collection of Polish, uh, a collection of oral testimonies that were in Polish for a researcher at the Holocaust Museum. This particular researcher was an undergraduate, could not read Polish, but was writing about a hospital that was in Krakow. And someone told her that there were about 100 testimonies that were in Polish that might talk about this particular hospital. She couldn't read Polish and didn't even know if those records would be useful at all. We used large language models to help her not only transcribe, but also translate the data found within them. And she was able to use those materials to then take them to a person who could effectively help her work through the Polish because she found the relevant material. In other words, the multilingual capabilities of these models can help make data more discoverable. And this also corresponds to what we call metadata curation. Oftentimes, when we're working with museums, such as the Holocaust Museum, we have millions and millions, in the case of the USHMM, hundreds of millions of images that have no metadata. In other words, we don't know anything about what's sitting inside of a particular archive of this size. So we might be missing very relevant information to research. One of the things that we can do is we can use large language models to help us automatically annotate and curate some metadata for these sources. But again, having a human in the loop that can go through and look at that data and validate it real quickly and click, yes, this is right, no, this is wrong, or make some adjustments. Making manual adjustments is much quicker and much more effective than oftentimes curating data from scratch. And just by giving just a few pieces of metadata, you can oftentimes help researchers find material that would otherwise be entirely missed. And then finally, I wanted to spend a little bit of time today talking about what we call retrieval augmented generation. This is a technique that has come out in the past year or so, and allows for us to combine the strengths of large language models and what we call vector databases. And it helps limit the chances for hallucinations or generating fake information in a response. It does not, however, eliminate that chance entirely. So how does this work, and what is it, and why is it useful? Well, if we look at this example here, I want you to start off by thinking about posing a particular question to a database. And this is the example of query down below. What a user might do is they might pose a question, such as, who was Fredegus of Tours? Now imagine that a large language model doesn't know that answer, but imagine that we've stored a lot of data about Fredegus in a database. One of the things that we can do is we can take that query and find the relevant documentation through a RAG system. We can go out and collect all the primary sources that mention Fredegus of Tours or describe something about him. Bring all of those sources together and then pass all the sources to the large language model along with that initial query. The large language model then has what we call the context necessary to answer that particular question. And this is where it can generate a response, but the chance for it generating a hallucination or incorrect answer is much more mitigated. It does not, however, go away. And this is where I wanted to kind of wrap up today to talk, hopefully give you a little bit of sense of where large language models really fit into the NLP landscape. And I've saved about, I think, 20 minutes or so that we can have some questions. And Stuart, I'm not sure what the typical format is here, if it's unmuting for questions or in the chat, but I'm open to either option.
Wonderful. Thank you. Thank you so much. Yes, I think we've peaked at we peaked at over 90 people. This is a really tremendous way to start off the term, and um, it's really all down to you. So we're tremendously grateful for that. Yes, so everyone, please type your questions in the chat, and I see we already have three or four, which is great. So maybe we'll just sort of dive in. Yeah, I think we can. So our first question regards synthetic data. I think we have a sort of synthetic data skeptic here, which is obviously a very understandable position to take. How to ensure the quality of the synthetic data is as quote good as the real data.
Sure. That's a great question. So we have a lot of ways of doing this. And this is again where human in the loop becomes very, very important. So in the case of the South African letters, one of the things that we did was we spent a good deal of time looking at about 1,000 examples of these letters that were very diverse. And we cultivated a list of the main features that we saw that appeared in the data. Some of the common experiences that we saw, some of the common themes. And then we looked at some other examples that kind of gave us a sense of what we would call edge cases or other things that were discussed. And so that gave us enough to really get a sense of what these letters contained as a whole without having to look at all 250,000 of them. And so one of the things that we did was we used all of that to ensure and guide the synthetic data so that it did reflect the real world data. So that was one case. And then we went through and manually looked at each of the cases that were coming out. And again, in this scenario, for something like NER, we don't need the data to be verbatim reflective of the original data. We needed to have the same kind of features and describing the same kinds of things and using the same kinds of labels that we wanted to see. So things like people, things like personal experiences. And we needed that to be highly varied. The other thing was these data they're written by predominantly South Africans who oftentimes English is not their first language, and yet they're writing in English. And oftentimes they would slip into Osa or Zulu or a Bantu language or Afrikaans. And so one of the features that we noticed about these letters is that frequently, and this is the case if you work with multilingual NLP, a speaker might switch back and forth between English and their first language. And so one of the things that we found is that particularly GPT-4 could generate very high quality instances of both Zulu or in any Bantu language or Afrikaans and switch back and forth as these speakers actually did. And to make sure that that data was reflective of the real world data, we have several speakers of Bantu languages on our project, and they were able to go through and verify that these phrases or words are being used correctly and being used as they would appear in these letters. So there was a lot of human in the loop with that particular project to make sure that the synthetic data matched the real world data.
Hmm.
Hopefully that helps kind of address that.
Yes, yes, yeah, absolutely. That's great, and I hope we can return to this question of multilingual DH at some point, as this is an area that I'm particularly interested in, and we at CUHK as Hong Kong's only bilingual university are obviously interested in this question as well. But we have another question here on sentiment analysis. Is it that by using LLMs we can identify not just the valence but also the extremity of the tone in a message in sentiment analysis, for instance?
Sure. This is a really good question. It's actually a very good, well-timed question. And the
Mm,
reason for this is because if we approach that question, it's a multimodal problem because
mm,
tone is audio, text is text, right? Um, so typically what you would do is you would use an audio to speech recognition model. So the common one to use would be Whisper. And this would take in an input audio signal and transcribe it. And if it's video, it's converting it to audio and just working with the audio. And you can get raw text output. Likewise, you can have a classification model that sits and then processes that output text and classifies different things as positive or negative. But so much of what we do, and please do correct me if I'm wrong, but I believe a lot of Asian languages rely on tone to affect the meaning of a particular word. And in English, we do this as well. Tone can radically, it can imply sarcasm. It can imply a lot of different things that are subtext that you can't actually do. About 2, maybe 3 weeks ago, a paper came out that actually combines both of these workflows. And it was dealing with named entity recognition, but the principles remain the same for classification of any type. So sentiment analysis is a classification problem. And what the paper showed was that by a model that could do both the ASR step and the classification step at the same time, both models improved. So the ASR model was able to improve its text output, so its word error rate, and the classification model was able to improve its F1 score, which is how you oftentimes will measure with precision and recall, balanced out for a classification model. And the reason for this is because the classification model was able to work with the tonal data, and the ASR model was able to work with the classification data. And so it was able to learn both features simultaneously. And that approach shows promise for using issues of tone and ASR during the transcription process for also doing the sentiment analysis simultaneously, as opposed to what typically would be done, which is a downstream task. So I haven't tested this out myself, but I think that's where everything is going right now.
Mm, wonderful, wonderful. And so maybe, yeah, I want to pivot ever so slightly onto, I guess, kind of how students would begin to apply some of the things you've been talking about. And we have a kind of, I guess, almost a kind of classic question here. Do we have to have very good math skills in order to work with large language models, calculus, linear algebra, all that kind of good stuff? Um,
I
it's
love this
yeah,
question.
humanists and numbers. It's the yeah the fundamental questions often.
I
Yeah.
love this question. So if you were doing this 6 years ago, the answer would be most likely yes. Over the last 6 years, though, a few things have happened. Um, a lot of the um, a lot of the what we call NLP frameworks, or the ways in which you would interact with NLP or even machine learning generally, have become more and more accessible. So 6 years ago, it was a lot easier to build a neural network because you could do it with TensorFlow or PyTorch. Nowadays, to train a machine learning model, you really don't need to have much of anything. As long as you can cultivate the training data, there's frameworks out there where you can click a button and fine tune a model without any coding at all. And so I think particularly this day and age, it's easier than ever to go ahead and work with and fine tune models. The one thing that will be a benefit for you is having an understanding of the maths, is being able to understand what's happening behind the scenes. Sometimes this can be really helpful for not only understanding um, what needs to be gathered to help improve annotations or to improve a model, but particularly why certain mistakes might be occurring at all. But for the
Mm,
most part, no, you don't need maths anymore to work with machine learning, which is
mm.
really exciting.
Yeah, I mean, what about kind of, I guess, some sort of concepts? I mean, would you sort of suggest students, I guess, have a little, I guess, a sort of a concept dictionary maybe, and some sort of, elements of probability maybe?
Yeah, so
Yeah.
the best book out there for doing this, in my opinion, is I think it's actually the textbook for Keras. So Keras is a framework that sits on top of TensorFlow, and it's called Deep Learning. I think it's called Deep Learning with Python. It's by Francois Chalet, and the book is fantastic for working with Keras. It just came out with, I think, a third edition a few months ago. But the reason why I'm recommending it is because the first 3 or 4 chapters are all about just that. It talks about probability, statistics, linear algebra, but it only gives you the essentials that you need to know to understand what's happening behind the scenes. And it's meant for people who don't have any background at all in this. I think it's very useful for students, especially humanists, to really get a deeper understanding of what's going on.
Mhm, mhm. Yeah. And of course, we have to give a plug to your YouTube channel as well, which has a variety of tutorials from soup to nuts that really I think cover things in just the right amount of detail, I would say, and in a very engaging way as well. So that's great. Um, yeah, we have lots of other questions. I guess you can divide them into two sort of buckets. We have a lot of questions about data, so we definitely want to cover that. And then we have a lot of students kind of asking about, what can I apply this to? I'm a historian. We have one question. Um, Maybe if we sort of start with the data and then we kind of move on to some like applications to sort of bring it alive for the students. I mean, we have sort of a simple question, like where are we getting our data, right? We as humanists often don't think we have data.
Sure. So, especially historians are in a particularly challenging position because oftentimes when we are starting a research project, our data isn't digitized. For a lot of us, we might be working with typed documents or handwritten documents. And essentially, those aren't discoverable unless they've been transcribed. And I actually had one other slide. I was worried I didn't have enough time, so I kind of stopped, but I'll go ahead and share this now because I think this is particularly relevant. Um, what we call OCR, or sorry, handwriting text recognition, HTR, up until about a month ago was a relatively unsolved problem. The complexity of handwriting text recognition meant that in order to transcribe handwritten documents, you really had to have a lot of data um, for a particular script of a particular language of a particular hand. You also had to do things like region detection, line detection, and then do HDR on the lines, then reconstruct the page. There's a lot of steps. It was very clunky. It required multiple models to do. About 1 month ago, Alibaba, their data science team, Quinn, released Quinn 2 VL. And Quinn 2.5 just came out. It's got a vision encoder, so it's going to be coming out with a vision language model as well. This is a branch of new models that have been coming out really for the past year or so. They've been out for longer, but the best ones have been coming out for the past year. These are vision
Mm,
language models that are multimodal. They can work with images and text. But what makes this particular model amazing, there's a lot of things.
mm,
Thing that makes it truly amazing is that it can do handwriting text recognition on English, Chinese, every Western language I've been throwing at it remarkably well.
mm,
With a word error rate of what I've seen with even like handwriting of Romanian cursive has been a word error rate of like 10%, but with English, it's like at 5%. I've seen German where I've had pages that are just absolutely perfect. I've had places in English where it's transcribed something correctly that I, as a human, would have mistaken. Um,
mm,
and I have I found edge cases that it doesn't do well, but that's expected. So medieval scripts, I've built out a fine-tuning library that can transcribe, that can fine-tune these models to medieval scripts. My point
mm,
is that we're entering an age where data that used to be inaccessible for historians is going to become accessible, and this is already available now. I've actually right now I'm running a massive job to transcribe handwritten documents at the Holocaust Museum that's going to make all these texts more discoverable. And so the question of where do LLMs fit into this landscape of for the historian, it's here. It's being able to work with the initial stage of our data, which is oftentimes a digitized image of a handwritten or typed document that we can't search. VLMs are a type of language model because they can work with both vision and language, and they're able to get the benefits of both. And so when it's doing OCR or HDR, it's not just looking at pixels, it's also benefiting from its robust knowledge of language as a whole. So it can make
mm,
the best prediction as it's producing a transcription, both with using the pixels of the image itself, but also using the language that's found within those pixels. And so at this stage, you can actually use vision language models to do transcription, and once you have a transcription done, you can make all this data even more discoverable by putting in what we call a vector database and making it searchable through semantics. And this allows for you to essentially query a collection of records based on a semantic query as opposed to a verbatim query. And I believe this might be a good example. I think the app might be down, but hopefully it won't be. We've been updating it. Imagine I wanted to search for hunger across a collection of Holocaust testimonies. Okay, cool, it is working. I can search for the word hunger, and if we look in this example here, I've got a question that doesn't deal with the word hunger. Instead, it's the word hungry. And I only have a very small subset of the data, but we have the issue of thirst here. Now, not hunger,
Mm,
but hunger adjacent. And so this is only about 5 testimonies. But we're able to see by searching for hunger, we're able to get the concept of hunger. So, for example, the word starvation appears here, the absence of food. We're able to get that concept of hunger. And this is where I see historians really benefiting from machine learning. It isn't in using large language models to generate answers. It's in using machine learning to help make things more discoverable for our research so that we can then
mm.
generate the answers.
Oh, absolutely. Yeah. And yeah, and maybe we can kind of aggregate and visualize these kind of findings, and we can find connections between texts, not just individual instances. Yeah. There's a lot you can build on if you know that that sort of thing. So can I ask, how does this new VLM compare to, say, existing tools like Transcribus, which is commonly used by our students?
Sure. So Transcribus is great, but Transcribus has a couple challenges.
Mm,
First, Transcribus is paid for, so you have to have a
correct.
subscription.
Yeah.
Um, the other problem is that you can annotate a large collection of data in Transcribus, and you can fine tune a model, no problem.
Yeah.
That model, I don't believe they don't let you download that model and make it open source and shareable, but you can
Mm,
make your data open source and shareable. With this is entirely open source. So you can open source the data, you can open source the model itself. The other thing is that Transcribus, if I'm not mistaken, uses an older form of a neural network, which is based on Pylea for doing HDR, which is fantastic. It's very effective. But it has a couple limitations with it, mainly because it's not working on the whole page as a whole as an ingested document. It's also not a vision language model, which means that that particular model is working on the pixel level, um, which means there's other downstream tasks you can't do with that kind of neural network. You can't, for example, load up a collection of 10 images of a notebook that somebody, a handwritten diary, and pose questions to it. With this vision language model, you can, because it's very much a conversational multimodal model. The other thing is that these models, if they don't encounter text, they also have the ability to switch over and just describe the image that appears on the page. So maybe there's a picture in the middle of a diary. So instead of having an error message that says there's no text here, this will say, or just giving you a blank output, this will describe the image that appears on the page. Because
mm,
again, it's a visual language model. So there's a lot of advantages to this. And also it can be run entirely locally, so it's free.
mm.
And if you run it on inference on a GPU, in my experience, without optimization, you can process about 500 pages in about an hour on one GPU.
Oh, okay. Okay.
Oh,
Yes.
sorry, and one more thing.
Oh, please,
It can
please go.
it can be fine-tuned with very limited data. So, for
Mm,
example, I fine-tuned it on one use case. It was in English with only about
mm,
100 examples, and it produced a more consistent output
mm,
in the output that I wanted. It was able to learn medieval Latin and Latin scripts with about 10,000 examples.
mm,
And so there's a lot that you can do here. And the nice thing is, if we're working in Transcribus already, we
mm,
already have the training data to fine-tune a Qwen 2 model.
mhm. Okay. Yes, this is very exciting. We actually have a project here at our library on images relating to China in Western books, and kind of identifying what's a kind of historical China image, kind of often embedded within a larger textual context. So this sounds like something we can use in a number of different ways. So yes, this is very exciting, and another example of how quickly the field is developing. As we, as you say, these things change from month to month. Um, Wonderful. Okay. Maybe we can. I see we have one other question. So if we do not use audio files and only do textual analysis to discern the extremity of a message, e.g., I kind of like it versus I love it so much, then classification models should be sufficient for such tasks. This is a follow-up, I think, from your to the earlier
Uh,
answer.
yeah, so kind of, maybe. So let me say two things. I love it so much, and I love it so much. Those are two very different statements.
Mm,
One, I clearly love it. The other one, my tone indicates, probably don't. So I've expressed the opposite of that meaning by simply changing my tone. And so while on the surface, yeah, I think in most cases you probably would be right. But so much of what we convey as humans is expressed in body language and tone. So little of it is expressed in the text itself. And this is where vision language models are even more interesting. So for example, Quinn 2 can't ingest, it can ingest a video, but it can't ingest the video with the audio. And this means that when it does analysis on the video, it's only working on the video. But we're only probably a few months, maybe a year away from the ability to use video, audio, and text in the same model. And at that point, you'll have the body language, you'll have the tone, and you'll have the actual text to do that classification. This is going to happen. And if you look at the Quinn 2.5 model, it has the vision encoder, but there's also a separate Quinn model that has an audio encoder. So it could be next week. Who knows? This changes so frequently, but we're well within the scope of being able to do all of that. So while I think you're right, I think in most cases you could classify that pretty easily. There's a lot that is conveyed in tone and body language that would make that uh, improve that process.
mm, yeah,
Yeah, no problem.
wonderful. Yeah. Um, Yeah, I see we have another question relating to data and what the student is calling, yeah, dirty data. Maybe to give a concrete example. Um, we often download things from archive.org, and the OCR is just a sea of nonsense. How effective are LLMs in your experience in kind of cleaning these things up? Some people are very for using it, others are, yeah, I've seen less good results. So,
Yeah, so there's great work in this space, and I would recommend not using an LLM in this area. And I'll give you
mm,
a couple of examples of why. First of all, there's a much smaller transformer model that was created by a scholar out of Paris that works with French and English. And it's a
mm,
transformer model that's specifically designed to deconstruct bad OCR and get a better output. I don't see that as being, when it came out 3 months ago, it was very useful.
mm,
I don't see that being as useful now because I would recommend going back to the original data and re-OCRing it with either the newest version of Tesseract, which is how you would do it if it's type text. If depending on the type of type text, you might want to fine tune Tesseract, or just
mm,
using the Quinn model to do it. Quinn does
mm,
HDR, it does OCR even better. And you'll have, I promise you, much better results than whatever's coming out of archive because there's lots of problems there. The other reason why I wouldn't recommend using an LLM is because we did exactly this with
mm,
early modern Italian. And the early modern Italian was OCR'd. It was OCR'd quite well, but it probably had a word error rate of about 5 to 10%. And
mm,
so we wanted to use an LLM to clean it up. And it looked really good. It did a great job. It cleaned things up. The problem is LLMs are generative in nature, which means that they're predicting the most likely next token based on what
mm,
it's seen prior, which includes that original text. So your chance of hallucination diminishes because you're able to have that context, but it's still there. But the real problem were the silent little hallucinations that we didn't really catch until we started looking more closely. It
mm.
updated the late medieval, early modern Italian to modern Italian. And so
No.
while it didn't change the text, it altered it in ways that you wouldn't want if you're producing some kind of edition or trying to build
Hmm.
out a semantic search engine. And that's a really subtle, very subtle thing that you might not
Mm,
catch without really looking closely. But that potential is there, what makes me a little bit more cautious to want to use LLMs in this space when I can just use a different approach to solve the problem, which is going back to the original source material and re-OCRing it with a lot more constraints.
yeah. And here we couldn't use, I mean, specifically trained models. There are such things as kind of Latin BERTs and I mean, there is there potential in that direction, do you think, now or in the future?
Yeah, so if you're working with Latin, there is, and it depends on the quality of the text or the
Mm.
period of the text, there is a Tesseract fine tune called Early Modern Print that specifically works with early modern print editions. And
Hmm.
it has comparable results with modern OCR. So it can take in like a printed text from the 1600s, and it can work with all the ligatures and diacritics that you have in there.
Mm.
But for the downstream task of making sense of it, there is Latin BERT, which comes from Patrick Burns,
Yep.
and there's a couple other individuals working in this space. There's a lot more now than there were 3 years ago.
Mm.
But really, what we're seeing happen is the transformer model is great with Latin, but LLMs out of the box can handle Latin a lot better than most of these smaller transformer models
Mm.
for a
Okay.
lot of tasks.
And then yeah, and then when you're dealing with, I guess, historical instances of particular language, say you have your 16th century Italian or your medieval or your Dante in Italian, then yeah, that's just yeah, that's another whole kettle of fish. So, okay. Great, great. Okay. Um, I guess let's see. We maybe have another 10 minutes or so. Maybe we'll kind of deal with the final questions in the chat, and then there are a couple of sort of general questions I want to ask you um, um, before we sort of sign off. Um, One student was interested in kind of the ethical questions that were sort of, peppered through the second half of your talk. And maybe I can't find the question right now, but basically they were asking, I guess, for I guess sort of more general reflections on kind of the ethical use of LLMs and training LLMs on sensitive data in the kind of broadest sense.
Sure. So whenever you're working with sensitive data, LLMs, because of just how they work, become even more challenging. So working with sensitive data and machine learning was already a thorny issue to begin with. For example, if I had a machine learning model that could do NER on Holocaust testimonies, I, as a practitioner, can easily understand why a person might be accidentally flagged as a concentration camp. It just makes mathematical sense why that would happen occasionally. But imagine somebody who looks at an output that I've just accepted, and they're a Holocaust survivor or a family member of a Holocaust survivor, and they see them or their family members flagged as the very thing that they find most horrific in their life. This could be very traumatic. So there's a lot of issues with just applying machine learning in general to these kinds of data. But with LLMs, it becomes even trickier. And the reason why is because we oftentimes use LLMs to generate text. And the way, like I said, the way in which they generate text, they have the potential to hallucinate or generate factually incorrect information because they're really just working with data that they inputted or were given and then leaning on their knowledge of the world as a whole to generate the most likely next token in a sequence of tokens. And this means that they can generate wrong information no matter how many safeguards we put in them. So imagine that you're the Holocaust Museum and you've spun up a version of ChatGPT where people can ask questions about the Holocaust. One of the first things that you'll probably see happen are people try to do what we call jailbreaking, which is when you try to get the LLM to generate responses that you don't want it to generate. And this is sometimes done in an ethical way where you're trying to learn the limits of these models so that you can improve them. But in other instances, people do this for malicious intent. And so you can immediately see the problems of being some kind of authority and your model generating maybe Holocaust denial information because they've jailbroken in some capacity. This could be very traumatic and have a lot of ethical implications. Also, if you're working with sensitive data that deals with real people, you have a lot of legal issues, not just ethical. So imagine if somebody who is an actual Holocaust survivor is now being described in the role of a Nazi prison guard. This would be highly problematic and highly unethical, and also could lead to potentially serious legal issues as well. So there's a lot of challenges in using LLMs. The only place that I've seen LLMs being used in this generative workflow is with a RAG system, but even that has the potential for hallucination. The RAG system is nice because it allows for you to essentially find relevant information and get a description about it. And I see it being used more not on the front end of a university or a museum website, but rather behind the scenes where researchers who are not going to do jailbreaking can come in and use your system to help find relevant material for their research. Or maybe a student, a classroom of students can come in and ask questions about things in a controlled a classroom setting. And that's where I see LLMs being useful and really kind of those restrictions being absolutely necessary because the risk for hallucinations is never going to go away. It's built into LLMs and it's here to stay.
Hmm. Absolutely, absolutely. Um, So maybe we'll transition into the final sort of section of our event, and we normally sort of ask all of our speakers this, two sorts of kind of final questions. The first relates to where you would or how you would suggest students might get started, what should be their first point of call, if they're interested in kind of exploring or applying some of the things you've been talking about today. And then the second question is the kind of the fun futurology question. I mean, where do you see the field in 5 years? What are you most excited about? If there's a graduate student kind of wanting to find the next big thing, what do you think that might be potentially?
Sure. I love these questions. So the first one I would say, and this was true in my case, pick something that's interesting to you. So I got started down this whole path because I was writing a dissertation. I needed a way to automate the process of finding people in medieval Latin and building out a massive social network. There was no way to do that. There were a lot of problems with that task. Latin-based NER really wasn't a thing. And so I had to solve that particular problem. And I learned everything, or at least I started learning stuff just by trying to solve that problem. And I broke it down into smaller pieces and I would go off and I would try to solve each one of these smaller pieces. And so the point of this is I would start off by a real world thing. What is something that you're currently researching that you want to be able to do? Maybe you have a collection of handwritten documents that are in medieval German and you want a way to be able to go through and work with them and search them and query them in some new way and then maybe find all the people that appear in them. Start off by learning that first part. What do you need to what model do you need to transcribe them? Maybe the Quinn model will work. It probably won't. But what do you need to fix that then? And then transcribe the data. And then work through each different stage in that workflow until eventually, piece by piece, you start to solve that problem. But as you solve each component in that problem, you're going to inherently learn a collection of new skills. And what's really fun about this space is each time you start a new project, it'll be a completely different problem space, but you'll be able to benefit from all those things that you learned in the past and piece by piece apply them to different projects. So time and again, I find stuff that I did with medieval Latin being directly applicable to modern South African languages because a lot of the same issues that you have with medieval Latin surface, not because it's the same language, but because the methods for solving those problems are very similar because you're dealing with what we call low resource languages, which are languages that don't have a large representation in digital corpora. And so what I would say is use that problem as just a way to build out a quiver of skills that you can then not only use in your own research, but really hit the job market with after you're done with your research. So that's
Wonderful.
the first one. Should I answer each of these, like, let people ask questions and then go to the next
Uh,
one?
sure, yeah. Let's see. Yeah, maybe let's move on to the final one. It's getting late here.
Sure.
Yeah.
So if I were starting off today, the space I would be really going in on is VLMs, vision language models, um, and also ASR models and kind of that space. And the reason for that is because working with data after it's already become text, it's not a solved problem, but it's a really overpopulated space right now. But what's going to happen in the near future is there'll be need to apply VLMs to massive amounts of images that have been digitized but haven't been processed across the entire world. This is a problem that exists everywhere. And being able to effectively take in this data from an archive and generate meaning from it that doesn't have meaning right now, so no metadata, no transcription, nothing. This will be a very useful skill going forward. And even if, let's say, it becomes a simple process where there's one model that can ingest everything, process it, it's never that clean in the real world. You always are going to have to do little things when it comes to pre-processing the data or post-processing it. There'll always be a need, but understanding how that process works will be very useful, I think, going forward. And I see that being particularly the space that'll be really useful for humanists.
Mm. Yes, and I hope that maybe that the people trained in this will go into the archive profession, and that the people who are, I guess, in the management of large cultural institutions and in the policy sphere will recognize the value of these tools and not put out unnecessary roadblocks. I yeah I work quite a lot in large European public archives, and sometimes they can be a little bit slow to innovate. And so, yeah, hopefully Spain will pick this up nice and quickly to make my life easier. That's great. Okay. Well, I it's 8:25 here in Hong Kong, so I think we might draw things to a close. But it was a really fantastic way to start off our seminar series, a really tremendous turnout and a very, very engaging presentation. And it's always nice to meet a fellow recovering Latin or sort of post classical Latin philologist. So that's good. That's really, really good. To everyone who's here, do remember that we have our next event on October 7th with Daniele Macuglia from PKU. And then is every 2 or 3 weeks for the rest of the term, we have events culminating on March 7th with our Day of DH. So I hope to see you all at future events. Um, Good evening, good morning, good night, wherever you happen to be in the world. Bye, everyone.
Bye, everyone. Thank you so much.
Bye.
You. Bye bye.